Hello, everyone. Thank you for joining my presentation. My name is Paul Lee, and I'm currently a PhD student and research assistant at the Department of Naval Architecture, Ocean and Marine Engineering at the University of Strathclyde. The title of my presentation is Autonomous Collision Avoidance Control using Deep Reinforcement Learning for Maritime Autonomous Surface Ships. The contents of my presentation are an introduction to the background, the presentation of the following methodology and case study, the presentation of the results, and finally finish with some concluding remarks. Currently, the maritime industry is paving the way towards the new shipping 4.0 era through the extensive use of cyber-physical systems. The main cyber-physical system of this new era is the autonomous ship, also known as the Maritime Autonomous Surface Ship, which according to IMO stands for a ship to which a varying degree can operate independently of human interaction. With the emergence of autonomous systems, the responsibilities are expected to gradually transition from human operators to the autonomous ones. Specifically, the chief engineer is expected to be replaced by the autonomous machinery system, also known as the artificial chief engineer, and the captain by the autonomous navigation system, also known as the artificial captain. The autonomous systems are expected to perform various conventional functions, such as the navigation, lookout, collision avoidance, etc. However, a basic precondition is that they are able to perform these functions at least at the same level as humans, so that the autonomous ships can be at least as safe as the conventional ones. From the autonomous functions mentioned, collision avoidance is expected to be one of the most complex and challenging ones. Thus, a research question is proposed: how can the complex collision avoidance problem be controlled autonomously? In order to tackle the aim of this research, a methodology was developed that consists of the following steps. In the first step, a reference system was defined based on the case study specifics. In step 2, a digital twin of the defined reference system was developed. In step 3, the autonomous collision avoidance controller was developed that was trained in step 4. And in the last step, the controller was simulated and verified in various environments. The case study considers a short sea shipping vessel that has an autonomy level degree 4 according to IMO, which is defined as a fully autonomous ship that can make decisions and determine actions by itself. Some specifications of the investigated ship include an overall length of 175 meters, single-propelled, equipped with laser sensors of 32 points that measure the distance between the ship and the obstacles. The navigating area considers only static obstacles of the restricted sea area. A safety zone around the ship of radius 175 meters is considered. Finally, MMG model of 4 degrees of freedom models the maneuverability of the investigated ship. The ship's main objective is to navigate in this area and exit through the narrow north gates without colliding and by keeping the obstacles out of the safety zone. Deep deterministic policy gradient algorithm was used to develop the autonomous collision avoidance controller, which is one of the reinforcement learning algorithms. DDPG was selected due to its advantages of being an off-policy and model-free algorithm suitable for online control and continuous problem. Some specifications of the developed neural network include 400 units of the actor network and 300 units of the critic network. Laser sensors input data, which are the distances from the ship to the obstacles, was used as input to the agent, and the outputs were the action commands for the propeller revolution and rudder angle. For the training process of the agent, various reward functions were developed, such as the reward for heading, a reward for the distance from the final destination, and a reward for keeping the obstacles out of the safety zone. An approximate of 1,800 training episodes were required until a good convergence of the training process was noted. After the completion of the training process, the agent was simulated in the training environment. The simulation results revealed that the agent was able to control the ship in the restricted area by detecting the surrounding environments using the laser sensor points and exit through the north narrow gate while keeping the obstacles out of the safety zone. To further test the capabilities of the agent to control the collision avoidance in new environments prior unknown, the north gates were adjusted accordingly. In the first case, the order of the two narrow gates were changed, and it was noted that the agent controlled the collision avoidance to exit from the widest gate without violating the safety zone. A more challenging case were examined in the second case, where the wide exit was diminished and placed further on the right side. This case is more challenging not only because it requires greater maneuvering, but also because the difference ratio between the widths of the narrow and wider gates becomes smaller. Yet it was still noted that the agent was able to successfully control the maneuver despite navigating through these gates for the first time. The conclusions derived from this study include, first, that the DDPG algorithm is suitable for real-time control of the autonomous collision avoidance, and that it has great generalization capabilities, which means that it can use the knowledge acquired from previous training and make decisions in new environments. Second, it was concluded that the consideration of safety zone leads to safer collision avoidance maneuvers, such as choosing to exit through the widest gate and not choosing the shortest route, which is the optimal one. Thank you for your attention, and I will be awaiting for your questions and meaningful input during the Q&A session.
I have no questions online. Are there any questions for Paul in the audience? I would be tempted to just ask, like compare this to other works in the literature. What is the novelty in it? I'm thinking particularly with regards, I'm not sure if you have seen it, the work of Eivind Meyer and Adil Rashid did some work on reinforcement learning for collision avoidance.
Yeah, the basic novelty is that previous works on reinforcement learning control was based on keeping the track, a predefined track, or controlling a curved path. But in this work, we consider a safety zone for the autonomous ship, which has not been considered previously.
Okay, thank you for the answer. I guess there is one more question. Did you test using other target vessels, not only land?
Yep, thank you for the question. As you can see from the presentation, we haven't considered other target vessels and moving obstacles, and it will be part of the future work.
Okay, let's thank the speaker again.